problem number 1 from the Chapter 11 review packet. And we're trying to find the percent shaded. We have a regular octagon inscribed inside of a circle. To start off with, I'm going to draw that segment. This is going to represent the radius of the circle, and I'll call that length x. And then I'll go ahead and draw another one of those radii, and that will be x also. And we know the radius of a circle doesn't change. If we're to draw in each one of those radii, there would be a total of 8 of them. So I can take 360 divided by 8 to get that this central angle is going to be equal to 45 degrees. So now getting to the formula we're going to use. Percent shaded is area that's shaded. That's the area of the circle minus the area of the octagon. However, so it's only going to be 3/8 of that. And then this is divided by the area of the circle. So as we start calculating that, 3/8 area of the circle, that's pi times x squared, minus the area of the octagon. Well, if we can find the area of this one triangle and multiply it by 8, that gives us the entire area of the octagon. So then we have 8 times 1/2 x squared sine of 45, using the side angle side formula, and that's all over pi x squared. Now as we simplify that a little bit, that is 3/8 times pi x squared minus 8 times 1/2 is 4, 4 times 3/8 is 12 over 8, and that's going to simplify to 3 over 2 x squared times the sine of 45, all over pi x squared. At this point we can notice that all 3 of the terms, the first term, the second term, and the third term, all can be divided by x squared, so we divide by that to simplify it. So our temporary variable of x has been eliminated. One other thing that I see is that there's a denominator of 8 in the numerator, so we can multiply everything by 8. And at this point there's no other simplification that can be done, so go to the calculator and you get approximately 3.7%. In problem number 2, we want to find the percent of this entire object that's shaded. So in this case, our percent shaded is going to be the area of that little circle on the top divided by the area of the entire triangle. The area of the entire triangle can be found using side-side-side Hero's formula. The semi-perimeter is 10 plus 10 plus 8 divided by 2, so that's 14. So then the area is the square root of 14 times 14 minus 8, 14 minus 10, 14 minus 10. And if we simplify that, we have a pair of 4s, so a 4 can go to the outside. 14 times 6 is 84. 84 is 821. So the area of that triangle is 821. The area of the circle is going to take a little bit more work. We're going to start by finding the radius of this big circle at the bottom. And to do that, we need to know that to find this point M, it's going to be the in-center of the triangle, which is the intersection of the angle bisectors. We're going to find out the measurement of angle I, and once we have angle I, then we can bisect that angle to get this right triangle. So in this triangle, measurement of angle I, we're going to use law of cosines. 10 squared equals 10 squared plus 8 squared minus 2 times 10 times 8 cosine of angle I. And using the law of cosines, we get measure of angle I is approximately 66.4 degrees, and we'll store that as letter A. Now that we know that, we can divide that by 2, and that will give us the measurement of this angle. And then in this right triangle we have at the bottom, we now know a few pieces of information. We know that this length is 4, because this segment is being bisected because it is an isosceles triangle, and we also know this angle, so using trig we can find this length, which I'll call x. So the tangent of measure of angle MIN is equal to opposite of x divided by adjacent of 4. And in solving this, we get that x is approximately 2.62, and we'll store that as letter B. The reason why that's going to help is because if we draw in segment NO, the entire diameter, we can double this B, and we get that what we'll call C is approximately 5.24, and that's the length of segment NO. Now we can start working on this upper triangle that I'll shade in turquoise right now, because the circle that we actually want is inscribed inside of that small triangle, so we're going to do the same kind of process on this triangle to find the radius of that circle. Going back to the entire triangle, we're going to draw in the entire height of that triangle. So we have triangle LNI, and what we know about that triangle is that this length is 10, this length is 4. So if we use Pythagorean theorem, 4 squared plus ln squared equals 10 squared, we get that ln is the square root of 84. So then the length of segment LO is equal to the square root of 84 minus the length of segment ON, which we just figured out was that 5.24. Evaluate this, LO is approximately 3.93, and we'll store that as alpha D. Now we're just focusing on this isosceles triangle at the top of the entire drawing, and we know that the length of RO is the radius of that circle, and we're going to look at this smaller triangle in order to find the length of RO. Now because we have parallel lines here, we know then that we can get this angle congruent to the same as the measurement of angle MIN. We already calculated that before, so we can use that information and start solving more of this triangle. So what do we know about that triangle? We want that value of x. Points W. We don't know the length of segment WO, but we can find it. Using triangle LNI and triangle LOW, I know that those triangles are similar. So using proportions in the similar triangles, I could say that the value of D over root 84 is equal to y over 4. So D over root 84 equals y over 4. Cross multiply and solve that equation for y. We get 4D over square root of 84 is equal to y. And then y is approximately 1.71. We'll store that answer as alpha E. Now that we know the length of this segment WO is equal to alpha E, that 1.71, we can start trying to find the radius of the small circle, which is the length of segment RO. So we know this segment, we know it's a right triangle. We also know that this angle, angle RWO, is equal to the measurement of angle MIN. So we can use trig to find this length. We'll call this value Z. So the tangent of measure of angle RWO is equal to opposite over adjacent. Solving that for Z, Z is equal to alpha E times the tangent of that angle. We don't have the measure of this measurement of this angle saved, but we do have measure of angle I is 66.4 that's solved as A. So to get this angle in the calculator, we're going to take alpha A and divide it by 2. Take the tangent of that angle and multiply that by alpha E to get that the value of Z, or the radius of that small circle, is about 1.12. We'll store that as alpha F. And that's important because now that we know the length of this segment, we can find the area of that small circle, which is what we've been looking for. So the area of that circle is pi times alpha F squared. And we're going to divide that by 8 square root of 21. And this comes out to about 10.8%.